The second domain is experimental design and data analysis plan. What's the purpose of this domain? It is to assess the experimental study design and analysis performed by the authors. Here we refer to the study authors. Particular aspects assessed are random errors and measurement errors. And what are these? The explanation and details for these random errors and measurement errors are provided before the relevant signaling questions. So you don't need to wonder about what we mean by random errors and measurement errors. Okay, first we explain the concept of random errors. Now, take a fair coin. Now, what's a fair coin? A fair coin is a coin which gives 50% heads and 50% tails when you toss the coin for a lot of times. Compare this with something called a loaded coin, which is slightly weighted on one side. For example, during minting, the weight of the coin was not balanced, so it's heavier on one side. Or you can apply a little bit of wax on one side, which makes the coin heavier. So in that situation, you won't get 50% heads and 50% tails. But here we are talking about a fair coin, and if you take a fair coin and toss it 10 times, you would expect that if the person who tossed the coin did not have any bias, you would expect that there is 50% heads and 50% tails. But this is not the case all the time. Sometimes you get 4 heads and 6 tails. Sometimes you get 3 heads and 7 tails. Sometimes you get 7 heads and 3 tails. Okay, so in fact, if you repeat the coin tosses, and there are 10 coin tosses for each experiment. If you repeat this experiment 25 times, only 5 times out of 25 do you get 5 heads and 5 tails. So that's only 20% of the times. So only 20% of the times you get 5 heads and 5 tails. 40% of the times you get 4 heads and 6 tails. 40% of the times you get 6 heads and 4 tails. 30% of the times you get 3 heads and 7 tails. 30% of the times you get 7 heads and 3 tails, and so on. So you can see that even in the absence of any design by the coin tosser, to get either heads or tails, there is variation in the number of heads, percentage of heads and tails you get between different experiments. Now, if you repeat this experiment more than, let's say, 50,000 times, you would get approximately 50% heads and 50% tails. So if you increase this sample size, then the percentage of times that you get the true value will also increase. And of course, if you are going to use 50,000 heads, 50,000 tosses, then it is going to be nearly 100% of the experiments that you will get 50% values. 50% heads and 50% tails are very close to that. Okay, so this phenomenon where even without any other reason, there is a difference between the true value and the observed value. So the true value is 50%, but you are observing 40%. There is a difference between the true value and the observed value. This is called random errors. And there is no other explanation. It just happens by chance. Okay, so that is called random errors. And there are two types of random errors here. One is the type 1 error or the alpha error. This is erroneously accepting that there is a difference between the samples when there is no difference in reality. In other words, erroneously rejecting the null hypothesis. Null hypothesis means there is no difference between the two samples. So null means zero, hypothesis theory. So there is no difference between the two samples. But you observe some differences between the samples, and this difference is simply because of random error. So just the same way, sometimes you get 30% heads. So let's say in one experiment you observed 30% heads, in another experiment you observe 70% heads. This, of course, could have happened by chance, as we just saw in the previous slide, but the authors are concluding that there is a difference between the first experiment or the first sample and the second sample. So they have erroneously accepted that there is a difference between the samples when there is no difference in reality. That means they have erroneously rejected the null hypothesis. And the type 1 alpha error is also called false positive, and it is the same as p-value. So you would find a lot of studies, almost all studies will say, oh, the p-value was less than 0.05. What does that mean? It means there is less than 5% chance that the difference that we have shown between the two samples is actually due to random errors. That's what they are saying. Type 2 error or beta error is erroneously accepting that there is no difference between the samples when there is a difference in reality. In other words, erroneously accepting the null hypothesis. It is also otherwise called false negative. And it is it's related to power because power is 1 minus beta error. Now, the sample size calculations takes both errors into account. Of course, in the previous example, I said if you toss the coin 50,000 times or 100,000 times, you would get very close to the truth. But that number is unachievable either in animal research or in human research. So you look at the minimum sample size that will allow us to reasonably control for the type 1 and type 2 errors. So reasonably reduce the type 1 error and type 2 errors. Okay, now we go to the signaling question 2.1. The signaling question 2.1 is, did the authors describe sample size calculations? The sample size calculations are performed to control for random errors, and we just learned what these errors are, and are only applicable in preclinical studies that involve hypothesis testing. That means the study has to find out whether a treatment is likely to result in benefit or, for that matter, harm. It should involve some form of hypothesis testing, and that's when these sample size calculations are relevant. Of course, without a sample size calculation, you wouldn't be able to know what the beta error is. So that's why it needs to be there. So classify this as yes or probably yes if the authors have described the sample size calculation to justify the number of animals used to reliably answer the research question. Classify this as no information if the authors have not described the sample size calculation to justify the number of animals used to reliably answer the research question. So if they have not described, then classify it as no information. Classify this as no or probably no if the authors have used clearly inappropriate information during sample size calculations. For example, high alpha and beta errors, which are unacceptable. So usually an alpha error of p is equal to 0.05 and a beta error at least beta error maximum is about 10 or 20%. That's 0.1 or 0.2. In other words, the power is usually 0.8 or 0.9. So but the study authors have used inappropriately high alpha and beta errors or unjustified potential treatment effects. They claim that the treatment effect reduces the outcome by 100% or 90%. without any justification. Of course, the treatment may completely decrease mortality. Okay, there may be treatments like that, but they have to be justified. So in the sample size calculations, they have used unjustified potential treatment effects. Signaling question 2.2, did the authors plan and perform statistical tests taking the type of data, the distribution of data, and the number of groups into account? Now, the statistical tests are performed to actually find out the alpha error usually. And the statistical tests that are performed depend upon the type of data. For example, categorical nominal data or ordinal data and so on. So there are different types of data, and the statistical tests actually depend upon the type of data, distribution of data. For example, is it parametric distribution, binomial distribution, and so on, and the number of groups compared. The authors may use multivariable analysis. What is multivariable analysis? It is an analysis that involves more than one predictor variable. So in a univariate analysis, you are looking at whether there is a difference between the groups based on the intervention. But in a multivariable analysis, you are looking at the more than one variable that can determine the outcomes. Or multivariate analysis. Multivariate analysis is where analysis involves more than one outcome variable. But quite often these two terms are used interchangeably. But here, when they do the multivariable analysis or multivariate analysis, there are some assumptions made about the data. The results are reliable only when these assumptions are made. Okay, so based on that, how do we classify the signaling question? Classify this as yes or probably yes if the authors planned and performed statistical tests taking all the type of data, distribution of data, and the number of groups compared into account, i.e., they justified the use of the test and reported about the assumptions in multivariable or multivariate analysis, and that's only if applicable. Okay, if they did multivariate or multivariable analysis, then they should report about the assumptions. Now, if there is no information, the authors did not, in other words, the authors did not report the reason for using the specific statistical tests, or they didn't mention whether the multivariable or multivariate analysis were met, then classify this as no information. Classify this as no or probably no if the authors clearly used wrong statistical tests. For example, the data appears non-parametric, but then they have used a parametric test. Or they clearly reported that the assumptions of multivariable or multivariate analysis were not met. Signaling question 2.3, did the authors make adjustment for multiple hypothesis testing? What do we mean by this? Okay, when you test multiple theories, when multiple hypotheses are tested in the same research, statistical adjustments are necessary to achieve the planned random errors. Okay, testing for more than two groups is a form of multiple testing. The statistical output usually adjusts for more than two groups. However, testing many outcomes is not usually adjusted in the statistical software output and has to be adjusted manually or electronically using some form of correction. Now, the additional explanation is that it's not necessary when the study authors have a single primary outcome and base their conclusions on the observations on the single primary outcome. However, when there are multiple primary outcomes, or when conclusions are based on secondary outcomes, when a single primary outcome was used, adjustments have to be done. Adjustments for multiple hypothesis testing have to be done. Okay, some examples. Um, if the effectiveness of a drug against cancer is tested by apoptosis, cell proliferation, and metastatic potential, authors should consider statistical adjustments for multiple testing. That's one situation where you're having multiple outcomes. So you should do adjustments for multiple testing. Multiple analysis of the data with the aim of stopping the study once statistical significance is reached, and multiple unplanned subgroup analysis to identify an analysis that's statistically significant should be avoided. Now, this is called data dredging or p-value fiddling or p-hacking, where authors say they kept recruiting subjects to the study until statistical significance is reached. So they just kept testing the data until statistical significance was reached. This should be avoided. Now, if you want to do interim analysis, there are methods that have to be appropriate methods that are available. So methods for interim analysis to guide stopping of clinical trials, such as sequential and group sequential boundaries, are available and can be implemented in animal research to improve efficiency. So if you really wanted to reduce the number of animals, you can use standard methods for interim analysis that are used in clinical research. Okay, how will you classify this question? Classify this as not applicable if multiple hypothesis testing was not performed. In other words, there is just one single primary outcome based on which the conclusions were made. Classify this as yes or probably yes if the authors made statistical plans to account for multiple testing and avoided data dredging or p-value fiddling or p-hacking, whichever way you want to call it. Okay, they already made some statistical plans to account for multiple testing. For example, they had interim analysis and they made some adjustments, used appropriate methods to do that. Or when they are doing multiple testing, multiple hypothesis testing for multiple outcomes or multiple time points, they already have adjusted that. Classify this as no information if the authors did not report whether they made statistical plans to account for multiple testing, or it was not clear whether they avoided data dredging, p-value fiddling, or p-hacking. Classify this as no or probably no if the authors clearly performed data dredging, p-value fiddling, or p-hacking. Usually they say we aimed to stop the study once statistical significance was reached. Or they performed a lot of unplanned subgroup analysis to identify an analysis that is statistically significant. The next signaling question is if a dose response analysis was conducted, did the authors describe the results? Now, what is dose response relationship or dose response analysis? So in pharmacological testing in animals, it's usually possible to test multiple doses of a drug. This may also apply to some non-pharmacological interventions where one can test the intervention at multiple frequencies or duration. For example, exercise for 20 minutes versus exercise for 10 minutes versus no exercise. A dose relationship indicates that the effect observed is greater with an increase in the dose. Animal studies incorporating dose response gradients were more likely to be replicable in humans. So how will you classify this question, signaling question? Classify this as not applicable if the study authors used a single frequency, duration, or dose of the intervention as applicable. Depends upon whether it's a pharmacological intervention or non-pharmacological. Classify this as yes or probably yes if the authors reported the dose response analysis if it was conducted. Classify this as no information if it was not clear whether a dose response analysis was performed even though they used multiple frequencies, durations, or doses of the intervention. So they actually report that they compared multiple doses of the drugs, but they don't report whether a dose response analysis was performed. That's when you would actually say no information. If they clearly conducted a dose response analysis but did not report it, then you would actually call it no or probably no. Okay. Now, the notice here, you just the authors have to just say that they conducted, right? They don't have to show that there was a dose response. I mean, they conducted and report the results. You don't need to actually see that there was a dose response relation. It will allow us to make a judgment how likely the results are translatable or clinically transferable. Okay, now we go to some measurement error issues. And one type of measurement error is accuracy. Now, signaling question 2.5 asks, did the authors assess and report accuracy? Now, what is accuracy? Accuracy is the nearness of a measurement to the true value. Now, pretend that this is a shooting range and this is the shooting target. And in the shooting target, you have what's called a bullseye. That's the center of the target. And you score more marks if you hit the center as compared to the outer circles. So an accurate value would be in the center, in the bullseye. So nearness of the measurement to the true value is an accurate value. The farther away from the center you go, it's less accurate. So if the authors used a new method of measurement, the accuracy of the new method is usually measured by testing what's called a reference material with known value. And they test the value using some gold standard method, and they assess how close the value is as measured by the new method compared to the gold standard method. So let's say you have a gold standard method. The gold standard method is, let's say you are assessing paralysis. The gold standard method, let's say, is clinical examination by a panel of experts. Now, the new method of measurement might be a gait test. So, and that gait test is you can see how many times it identifies limb paralysis correctly as compared to what the expert identifies. Now, depending upon the type of outcome, accuracy can be assessed by various statistical measures. And the study authors may use a method for which the accuracy is previously known. So that is also acceptable. So if they are using a new method, then they should report how accurate it is using one of the statistical methods mentioned here, or they might use a method for which the accuracy is already known. Both are acceptable. Okay, so classify this as yes or probably yes if the authors provided a measure of accuracy by using an equipment with known accuracy information or used a reference material to assess accuracy. Okay, so either of these are acceptable. Classify this as no information if it was not clear whether the authors used an accurate method or measured accuracy. Classify this as no or probably no if it was clear that the authors measured the accuracy, for example, by using a reference material, but did not report the results. Now, it is not sufficient if the authors simply say that used a highly accurate equipment without providing the detailed accuracy information, even if they provided a reference. Okay, so they provided a reference, but they did not provide what the accuracy was from that reference. In such situations, classify this as no information rather than yes or probably yes, because we don't know what highly accurate means. So that author might say the accuracy was 50% and it was highly accurate. We don't know that. So they need to provide some numbers. Okay, so the next signaling question is related to precision. Did the authors assess and report precision? What do we mean by that? Precision is the nearness of values when repeated measurements are made in the same sample. That's called technical replicates to each other in the context of measurement. Okay, so this isn't precision has other meanings when used in the confidence interval setting. Here, in the context of measurement error, we are talking about nearness of values when repeated measurements are made in the same sample. So here you can see that all the shots are close to each other. That's precise. And these shots are far apart from each other and they are less precise. Now you can note that none of these shots are close to the bullseye. So that means an intervention or a test could be very precise, but may not be accurate. It simply indicates agreement between a set of repeated measurements or repeated experiments. So the same methods for using accuracy can be used for assessing precision, except that instead of using a reference material, which was the gold standard reference material or a gold standard test, the comparison is between the measurements made in the same sample for assessing precision. Okay. The width of the confidence intervals also provide a measure of precision. So they do lots of measurements and they provide confidence intervals for these measurements that will give an idea of the precision as well. So classify this question as yes or probably yes if the authors performed repeat measurements on the same sample and reported precision. Classify this as no information if the authors did not mention about performing repeat measurements on the same sample. Classify this as no or probably no if it was clear that the authors performed repeat measurements on the same sample but did not report the precision. So the next signaling question is 2.7. Did the authors assess and report sampling error? Now, errors arise because of the non-homogeneous nature of the tissues or change of values over time. For example, diurnal variation. Now, the same methods used to assess accuracy can be used for assessing sampling error, except that instead of using a reference material, the comparison is between measurements made in samples from different parts of the cancer or disease tissue. These are called biological replicates or samples from different times. Now, in the previous signaling question, precision, we are talking about measurements made in the same sample. In this signaling question, we are talking about measurements made in samples from different parts, or it could be samples from different times. Okay, so classification, classify this question as yes or probably yes if the authors perform measurements on samples from different parts of cancer or disease tissue, or samples from different times and actually reported what the sampling error was. Now classify this as no information if it was not clear whether authors performed measurements on on samples from different parts of the cancer or disease tissue, or it was not clear that they took samples from different times. Classify this as no or probably no if it was clear that they actually performed repeat measurements. When I say repeat measurements, sorry, when I say measurements here, measurements on different samples, but they did not report the sampling error. That's when you would classify this as no or probably no. So they have made the measurement, but they did not report it. Okay. Now, in the previous questions, we were not assessing whether the measurement error was low or anything at all. We were just finding out if the measurement error was reported in the last three signaling questions. Uh, in this signaling question 2.8, which is the last signaling question for this domain, was the measurement error low or was the measurement error adjusted in statistical analysis? Okay. Now, what is a low measurement error? Um, there are no universally agreed values at which measurement errors can be considered low. This will depend upon the context and the measure used to assess measurement error. For example, if the difference between the groups is in centimeter and the measurement error is non-differential, that is, it doesn't depend upon the intervention, and it is actually only a fraction of a millimeter, then measurement error is unlikely to cause a major difference in the conclusions. Okay, so the measurement error is not different between the two groups because for example, somebody might have used an accurate instrument in the intervention group and a non-accurate instrument in the control group. That is differential measurement error. So here measurement error is non-differential. They are using the same test in both the groups, and the difference between the groups is in centimeter, whereas the measurement error itself is a fraction of millimeter. Then it's unlikely to cause major differences in the conclusions. On the other hand, if the measurement error is differential, that is, the measurement error depends upon the group in which the measurements were made, or large relative to the estimates. So the difference between the groups is in millimeters and the measurement error is in centimeters. Then this should be estimated and adjusted during the analysis. Now, measurement error can be adjusted using special methods such as ANOVA repeated measurements, general linear model of repeated measurements, regression calibration, moment, moment reconstruction, or simulation, extrapolation, and so on. Okay, so there are specific methods, and we want to find out if the authors have used some of these methods to adjust the errors. Okay, so classify this as not applicable if it was clear whether measurement errors were assessed. That is, you have to have a no information for all three questions if it was not clear whether they actually measured it. So you have to have no information for questions 2.5, 2.6, and 2.7. Then you would classify this as not applicable. Classify this question as yes or probably yes if all the measurement errors, it should cover errors in accuracy, precision, and sampling error, were low. It's not sufficient if only one of them is low. It should be all of them low. Then, or if the authors reported that the measurement errors were adjusted in statistical analysis, then you would say yes or probably yes. Classify this question as no information if it was not clear if all the measurement errors were low or if any of the measurements were high. Okay, so even if one of them were high, then you would classify this as no information if it was not clear whether the authors adjusted measurement errors in statistical analysis. So in other words, okay, we have some measurement errors that were high, but it was not clear whether the authors adjusted the measurement errors in statistical analysis. Now classify this as no or probably no if it was clear that measurement errors were measured and at least one of the measurement errors were not adjusted in statistical analysis if they were high. Okay. Just a little bit of summarization, I think, because of the complex words that are used, a little bit of summarization. So if it was not clear whether measurement errors were assessed, That means you have answered no information for all three questions, 2.5, 2.6, 2.7, then it's not applicable. Now, if it was clear that measurement errors were assessed and then they were low, then you would classify it as yes or probably yes. If it was adjusted using statistical analysis, using special methods for adjustment of measurement errors, then you would classify this as yes or probably yes. Now, if at least if one or more measurement errors was high, then you should find out if the authors have adjusted the measurement errors in statistical analysis. And if it was not clear, then you would classify it as no information. And if it was not clear, if all the measurement errors were low, then you would also classify it as no information. Now, if at least one of the measurement errors were high and was not adjusted in statistical analysis, then you would classify it as no or probably no. Okay, so that's how this classification is done.